Hi, this is an example problem from chapter 24 on energy, density, and intensity of sunlight. Pause for a moment to read the question. All right, so the numbers used in this example are real world numbers. This is what the sun produces roughly. So it enters the top of the atmosphere and it has an electric field with an RMS value of 720 newtons per coulomb. That RMS is kind of your average value because we know the electric field for an electromagnetic wave is oscillating sinusoidally back and forth very rapidly. Part A says calculate the average energy density of this wave. All right, to do that, we're going to have to look up an equation for the average energy density of a wave, and here it is. Let's go ahead and copy this over real quick. So we can see that the average energy density here, which we call U bar with an average on it, it depends on the electric field RMS value and the magnetic field RMS value. We know that this is just a constant and this is just a constant we can look up. However, I want to show you that there's an easier way to do this sometimes. The values ERMS and BRMS are related, and so we can rewrite the value of U average in terms of either just the electric field or the magnetic field. So to see real quick how that works, let's just look at a few things. So ERMS is equal to C times BRMS. Where C is the speed of light. We can also write this. For the speed of light, it's also given by 1 divided by the square root of these two constants squared. And so that in itself is interesting, that these two constants, one for electricity, another one for magnetism, put them together, they give you the speed of light in a vacuum. Now let's go ahead and simplify this a little bit. So I want to go ahead and write we know ERMS, so let me go write the BRMS in terms of the ERMS. So BRMS from the first equation, that is equal to ERMS divided by C, which combined with the other equation that we just wrote for the speed of light, that becomes ERMS divided by C is going to be multiplied by epsilon naught mu naught, since that's a reciprocal. Now we're going to go ahead and square both of these. So BRMS squared is equal to this whole thing squared. And what do we get? We're going to end up getting E RMS squared multiplied by epsilon naught times mu naught. And if we put that into the equation, let's see what we end up getting here. So we can also write U average as epsilon naught over 2 ERMS squared plus 1 over 2 mu naught. Now I'm going to plug in for BRMS squared. Forgot to put a square on that. And we'll notice we get some cancellation here. And so we end up with epsilon naught 1/2 ERMS squared. And again, epsilon naught 1/2 ERMS squared. This gives us a value for for U, the average energy density. It's going to be equal to simply epsilon naught times E RMS squared. By a very similar process, we can also show that we can also write this as BRMS squared divided by mu 0. And so if we want, we can write the whole equation. Mu is equal to epsilon naught over 2 RMS squared plus 1 over 2 mu naught BRMS squared. And so if you notice that these two are each half of the whole, and so the electric field and the magnetic field, they each store half the energy in the electromagnetic wave. Now for this part A here, since we know ERMS, I'm going to go ahead and just use this equation right here. So the average energy density, epsilon naught times E RMS squared. We have to look up epsilon naught. That's equal to 8.85 times 10 to the minus 12th, and that's going to be Coulomb squared divided by Newton times meters squared. And the ERMS value we've got here is 720 newtons per coulomb. When we calculate that, it comes out to 4.6 times 10 to the minus 6th. And what are the units? Well, this is energy per volume. And so I'm in SI units already, so I'm going to end up in SI units. It's going to be joules per meters cubed. All right, let's look at the next one here. So for part B, it says calculate the RMS value of the sun's magnetic field. Well, that'll be easy. We've already got the ERMS value. We know how they're related here. BRMS is equal to ERMS divided by C. So for part B, BRMS is going to be equal to ERMS divided by C. That's always the case. ERMS is equal to 720 newtons per coulomb. We're going to divide by C, the speed of light, 3 times 10 to the 8th meters per second. And we'll get an answer here of 2.4 times 10 to the minus 6th. What are our units? Well, I'm in SI units. It's going to come out to Tesla for magnetic field. Let's look at part C here. Part C says, calculate the average intensity of sunlight at the top of the Earth's atmosphere. All right, so energy density is U bar. The average intensity we write as S. And it turns out, if we look at the equation for that, that it is just equal to C times U bar, and the units work out to watts per meter squared. So C, the speed of light, times the average energy density, that's going to be 3 times 10 to the 8th meters per second, multiplied by our value for the average energy density. And when we multiply that out, we'll get a value for the average intensity, which comes out to about 1,400 watts per meter squared. And so that is exactly what the average intensity of sunlight is at the top of the Earth's atmosphere, more or less. As it travels down through the atmosphere absorbs and scatters some of that light, and so it gets reduced, the average intensity that actually reaches the ground. All right, let's look at the very last part here. So part D. The sunlight strikes a 0.75 meter by 1.5 meter rectangular solar panel on the ISS, the International Space Shuttle. The rays making a 30-degree angle with the normal line of the panel. How much total power strikes the solar panel? Well, let's set this one up so that we can go ahead and view this with an image. All right, so in part D, we've got little solar panels here. Let's imagine we've got a little solar panel here, and one of these guys has got an area. It's a rectangular, 0.75 meters by 1.5 meters. Oop, that should be a meter. All right, now I want to imagine that we have an incoming amount of solar radiation. It's got an intensity 1,400 watts per meter squared. It's going to strike one of these solar panels at an angle 30 degrees from the normal. So let's draw the normal line to one of these. Okay, so here we go, a little normal line like this. And now the light itself is going to be coming in like this. So I'll use purple for the light. It's shining down here, at an angle here of 30 degrees from the normal. And so to calculate the total power that's going to be striking that area, we can use a formula here. So again, this is the 1400 watts per meter squared. So the average power, P bar, that's going to be striking that surface, it depends on the geometry as we saw, and it depends on the area, and it depends on the intensity that's striking it. So here's your equation here. The average power is equal to the intensity times the area it strikes times cosine of the angle between the direction of the beam and the normal line, which takes into account the geometry. So in this case, we've got the average power. It's going to be equal to 1,400 watts per meter squared multiplied by the area, which is going to be 0.75 meters by 1.5 meters for the rectangle. And then we've got cosine of 30 degrees. Notice that if the angle had been 0, striking straight down onto the entire surface, that's when you get the max power, right? And so putting this to calculator, the power that is going to be striking that surface is equal to about 1,360 watts, or joules per second, as the meters cancel out here.